Hello, in this lecture, we'll prove that intersection of two quasi-convex subgroups in a hyperbolic group is again a quasi-convex subgroup. And using it, we'll prove that a hyperbolic group cannot contain an abelian subgroup of rank greater than equals to 2. So first, let us prove this theorem. Let H1 and H2 be two K quasi-convex subgroups in a hyperbolic group G. And let us take an element H in the intersection of these two groups H1 and H2 and join this 1 and H by a geodesic of the group G. So what will prove that if I take any vertex B of this geodesic joining 1 to H, so there exists a vertex B prime in H1 intersection H2 such that the distance between B and B prime will be less than equals to some function which of this K and the hyperbolicity constant of the group G. Okay. So for each vertex B in the geodesic joining 1 to H, so there exist vertices x belongs to H1, y belongs to H2, such that the distance between B and x is less than equals to K, and the distance between B and y is less than equals to K. So this is because this H1 and H2 are K quasi-convex. So this will imply that the distance between 1 and B inverse x, so that is less than equals to K, and the distance between 1 and B inverse y, that is less than equals to K. Now, let us take this B naught to be the number of elements in the ball of radius K around 1. So B0 square, it is equal to the number of elements in the Cartesian product of these two poles B1K. And now let us take S to be the generating set of the group G. So what will prove that if I take any vertex P in the geodesic joining 1 to H, the distance between the P and H1 intersection H2 is less than equals to B naught square. So this will prove that this H1 intersection H2 is a quasi-convex subgroup. Let gamma be a geodesic word representing the geodesic 1 to P. Now let us consider this set. So let us define this set omega. So this is the collection of all words W belongs to the free group generated by S, such that gamma concatenated with W, it belongs to H1 intersection H2. And for every prefix B of W, distance between gamma B and HI is less than equals to K, where this I is equal to 1. I is equal to 1 and 2. So let me draw a picture of it. So what is the set omega? So I have taken this H which belongs to H1 intersection H2. So join this 1 to H by a geodesic. And now let us take an element P in this geodesic. So this geodesic path from 1 to P is labeled by gamma. And so what is this set omega? So you take all those words in the free group generated by S. So W belongs to this free group generated by S, such that gamma followed by this W. So it will you'll get a vertex gamma W. So this land inside this H1 intersection H2. And if I take any vertex on this path, so which will be labeled by, so this subword will be labeled by u. This vertex will be gamma u. So distance of gamma u to h1 is less than equals to k, and distance between gamma u to h2 is less than equals to k. Okay, so we have defined this set omega, and this set omega is non-empty. So this is because, so if I take this, geodesic path joining P and H, suppose this geodesic word is labeled by W1. So this W1 will belong to omega, because gamma W1 is equal to H, and which belongs to this H1 intersection H2. And of course, because this H1 and H2 are quasi-convex, if I take any vertex here, so distance of this vertex to H1 or H2 will be less than equals to k. So therefore, this set omega is non-empty. Okay. So therefore, the set omega, so this is non-empty. And now let us take W naught to be an element of this omega, such that this word W naught of minimal length. So we can find an element of omega which is of minimal length. The claim is length of this W naught. So W naught, it is a word of minimal length in omega. So claim is the length of W naught is less than equals to V naught square. So if you can prove this thing, so then we are done. So if possible, let length of W naught is strictly greater than V naught square. So then, so what we have, so this gamma W naught, by the definition of omega, gamma W naught, it belongs to your H1 intersection H2. And by Bayesian hole principle, so we'll get two vertices, gamma u prime, belonging to this W naught, such that distance of gamma u to H1 is equal to distance between gamma u prime H1, and the distance between gamma u H2 is equal to distance between gamma u prime H2. So why this is true? So if I take this function, so let us consider this function. So function is defined from the vertex set of this W naught to this Cartesian product of this two ball. So f of gamma u is equal to the distance of gamma u to h1 and distance of gamma u to h2. So you take this ordered pair. So this first coordinate, it will belong to this ball of radius k around 1, because distance of gamma u to h1 is less than equals to k. And similarly for the other coordinate also, distance of gamma u to h2 is less than equals to k. Now the cardinality of the domain is equal to what? So it is equal to the length of this W naught, which is yeah, yeah, cardinality of this yeah, uh, yeah. So the cardinality of this domain set, it is equal to the length of this W naught, and what we have taken length of W naught to be greater than V naught square from here. So therefore, so we'll get two elements in the vertex set of this W naught, such that f of gamma u will be equal to f of gamma u prime. So this follows from the pigeonhole principle. The cardinality of the domain set is greater than the cardinality of the codomain set. So that's why you will get two vertices gamma u and gamma prime u in the vertex set of this W naught, such that f of gamma u is equal to f of gamma u prime. So therefore what we have here, so there exist two vertices gamma u and gamma u prime belongs to W naught, such that the distance between gamma u h1 is same as the distance between gamma u prime h1, and distance between gamma u h2 is same as the distance between gamma u prime h2. And we can take this subwords, this u and u prime of this W naught, such that that the length of this u is strictly less than the length of the subword u prime. Okay. So therefore, so there exist points xu prime belongs to h1, yu prime belongs to h2, such that distance of this gamma u to xu, distance of gamma u to xu, and distance of gamma u prime to xu prime, so they are same. So this two geodesics are labeled by same word. So that is the thing I have written here. So gamma u inverse xu is equal to gamma u prime inverse xu prime, and distance between gamma u to yu is same as the distance of gamma u prime to yu prime. So this xu, it lie xu and xu prime, it lies in h1, yu and yu prime, they lie in h2. And similarly, gamma u inverse yu is equal to gamma u prime inverse yu prime. So this already I have said this thing. So we have this following picture. So this word is labeled by W naught. So gamma W naught, it belongs to H1 intersection H2. W naught is the word of minimal length which belongs to omega. And we got these two vertices, gamma u and gamma u prime, on this path such that distance of gamma u to xu is same as the distance of gamma u prime to xu prime, and distance of gamma u to yu is same as the distance between gamma u prime and yu prime. And this xu prime, it belongs to H1, yu and yu prime, they belong to H2. Okay. So now there exist subwords V and V prime of W naught such that this W naught is equal to UV, and W naught again it is equal to your U prime V prime. So if I again go back to this picture, so this path is labeled by W naught, and so this path is labeled by W naught. So W naught is equal to U concatenated with this geodesic, so which is labeled by V. And again W naught is first this U prime and then concatenated with this part which I have called it to be V prime. Yeah. So this gamma W naught, so now this is equal to gamma UV equal to gamma U prime V prime, which belongs to H1 intersection H2. Now observe that from this equation, so from this equation, so xu prime inverse is equal to yu prime inverse. So this will imply xu inverse yu is equal to xu prime inverse yu prime. So this tells that, so from this picture, if I take the geodesic joining this xu and yu, so the leveling of that geodesic will be same as the geodesic joining xu prime and yu prime. Okay, so we have this observation, and now let us take G to be an arbitrary element of the group G. Now let us observe this thing. So distance between gamma ug to H1, so this is equal to the distance between G gamma u inverse H1, so which is same as the distance between G and gamma u inverse xu H1, as xu belongs to H1. Now from this equation start, so observe that distance between G gamma u prime inverse xu prime, so this distance is same as the distance between G gamma u prime inverse xu prime H1. So this is because of this equality. And this distance is same as the distance between gamma u prime GH1. And similarly, distance between gamma u GH2 is same as the distance between gamma u prime GH2. Now let us take, so G to be V prime. So we have taken this G to be an arbitrary element. So we can, in particular, we can take this G to be V prime. So therefore, distance between gamma u v prime h1, which is equal to distance between gamma u prime v prime h1. And because this thing, it belongs to h1, so therefore this distance will be equal to 0. Yeah, so if I put g equals to v prime, so if I put g equals to v prime in this equation, so we'll get this equality, and this distance is equal to 0. So this will imply that gamma u v prime belongs to h1. And similarly, gamma u v prime, it belongs to h2. So this will imply that, so both, so this element belongs to both this h1 and h2. So therefore, gamma u v prime, it belongs to h1 intersection h2. And this proves that u v prime, it belongs to omega. So now what we have here from this picture, so this part, you can pull it back to here. So u followed by this v prime. So u followed by some v prime. So this belongs to omega. So u v prime, it belongs to omega. And the length of this u v prime, it is strictly less than the length of w naught. So this contradicts the minimality of length of w naught. So therefore, so length of w naught is less than equals to v naught square. And pw naught, it belongs to h1 intersection h2, and distance between p and pw naught is less than equals to v naught square. So therefore, we have proved that this h1 intersection h2 is a quasi-convex subgroup. And now, so as a corollary, we have the following things. So let us take G to be a hyperbolic group with an element G such that order of that element G is infinite. So first observation is, if I take this map from Z to G, n goes to G to the power n. So this map is a quasi-isometric embedding. And the second thing, so this requires a proof. If I take the subgroup generated by G, so this is an infinite cyclic subgroup. So the subgroup has finite index in its centralizer. So in particular, a hyperbolic group, it cannot contain this Z cross Z. If it contains Z cross Z, so then if I take the generator of, suppose this Z, so that will be an element of infinite order. And if I take the centralizer will contain Z cross Z. So this property will be violated if G contains Z cross Z. So the centralizer, because it contains Z cross Z, the index of that cyclic subgroup will not be of finite index in the centralizer. So therefore, so this hyperbolic group G, it cannot contain Z cross Z. Okay, so let us first prove the first thing, that this map Z to G, n goes to G to the power n, it is a quasi-isometric embedding. So we already have seen this thing, that this centralizer of an element is quasi-convex, and hence it will be a finitely generated group, and it will be also hyperbolic. So let us take CG to be generated by this A1 AK. So first claim is, the center of the centralizer, it is the intersection of the centralizer of AI. So AI is the generating set of this centralizer. So how do you prove this thing? So let us take X to be in the center of the centralizer of G. So this means that it will commute with every element of the centralizer. So in particular, XAI will be equal to AIX. So x belongs to CAI for all I 1 to k. So therefore, center of the centralizer of G is contained in this intersection. And now converse part, if I take any element in this intersection, so YAI equal to AIY for all I equals to 1 to k. And now let us take any element x belongs to G. So x can be written as this product of this AIs. And if I take x, y, so which is equal to this thing, and y commutes with every generator's AIs. So therefore, this element will be equal to this element, and which is equal to yx. So therefore, x belongs to the center of the centralizer. Okay, so now every centralizer of this generator is a quasi-convex subgroup of the hyperbolic group, and the center of the centralizer, it is the finite intersection of quasi-convex subgroups. So therefore, this will be again a quasi-convex subgroup of G, and hence it is a hyperbolic group. Okay, so this is an exercise. One can show that if I take any abelian group which is hyperbolic, then it will be virtually cyclic. Virtually cyclic means it has a cyclic subgroup of finite index. That is the meaning of virtually cyclic, and the converse is obviously true. Okay, so therefore this group, because it is an abelian group, and we have proved that it is a hyperbolic group, and from this exercise, so this will be a virtually cyclic group. That is, there exists a cyclic subgroup of finite index in the center of the centralizer. So this will imply that this index of this infinite cyclic subgroup in the center of the centralizer is finite. So, and this will imply that this cyclic subgroup is quasi-convex in the center of the centralizer. Okay, so this is a quasi-convex subgroup of the center of the centralizer. So therefore, by a previous theorem, so the embedding of this cyclic subgroup in the center of the centralizer will be a quasi-asymmetric embedding. This again we have proved it is a quasi-convex subgroup of the centralizer. So this embedding will be quasi-asymmetric embedding. Centralizer of an element is a quasi-convex subgroup. So therefore, this embedding will be quasi-asymmetric embedding. So therefore, what we have proved that this infinite cyclic subgroup is quasi-asymmetrically embedded in the hyperbolic group G. So therefore, so we have proved this this fact that the map from Z to G, n goes to G to the power n, it is a quasi-asymmetric embedding. Okay. And next, what we want to prove that, so this subgroup, infinite subgroup, has finite index in the centralizer. So that we want to prove. Okay. So first we show this thing. So if G to the power P is equal to this conjugate T G to the power Q T inverse, so then mod of P is equal to mod of Q. Okay. So suppose T inverse GPT is equal to GQ. So this will imply that T inverse GMP T is equal to GMQ. And this embeddings, just now we proved that these are quasi-isometric embeddings. So this we have proved. Okay, also observe this thing. So t to the power minus m, g p to the power m times t to the power m is equal to g to the power q to the power m. So observe this thing. So this is an exercise. Okay. So now let us assume mod of q to be strictly greater than mod of p. Okay. So there exists k greater than equals to 1, epsilon greater than equals to 0, such that 1 by k mod q to the power m minus epsilon is less than equals to distance between 1 to gq to the power m less than equals to 2m distance between 1 to t plus distance between 1 g p to the power m. Okay. And this thing again less than equals to 2m distance between 1 to t plus k times mod p to the power m plus epsilon. Okay, so this inequality here, it follows from the fact that this embedding is k epsilon quasi-isometric embedding. And what about this inequality? So g q to the power m is equal to t to the power minus m g p to the power m t to the power m. So therefore, distance between 1 to gq to the power m will be less than equal to the length of this word, and which is equal to this thing. And now again, distance between 1 to g to the power p to the power m is less than equals to k times mod p to the power m plus epsilon. This follows from again the fact that the embedding z to g, m goes to g to the power mp, it is a quasi-isometric embedding. We can take it to be k epsilon quasi-isometric embedding. So therefore, what we have now, so 1 by k times mod q to the power m minus k times mod p to the power m is less than equals to 2m distance 1 to t plus 2 epsilon. And also note that p belongs to z and p not equal to 0. So this will imply that mod of p is greater than equals to 1. Now from here, so what we have, so 1 by k mod q by p to the power m minus k is less than equals to 2m times distance 1t plus 2 epsilon, because mod of p is greater than equals to 1. The left hand side of the inequality is exponential. So we have taken mod of q to be greater than p. So left hand side is an exponential and the right hand side it is linear. So there is a contradiction. So contradiction because of this fact. So similarly, we can prove that mod of q is not less than equals to mod of p. So therefore, mod of p is equal to mod of q. We have shown. Okay. So this will imply that positive powers of G have distinct conjugacy class. So this will follow from this thing. So we have shown that 0 to the power p, if it is equal to t 0 to the power q t inverse, so this will imply mod of p is equal to mod of q. Yeah, so if I take P and Q to be positive, so they cannot be, and if they are distinct, so they cannot be conjugate to each other. So this implies positive powers of G have distinct conjugacy class. So therefore, by taking suitable powers of G, we can assume G is not conjugate to any element of the ball of radius 4 delta with center 1. Okay. So now next claim is, if I take any element x belongs to the centralizer, so distance of x to the cyclic subgroup generated by G will be less than equals to twice distance between 1 to G plus 4 delta. So we want to prove that the index of the cyclic subgroup generated by G is finite in the centralizer of this element G. Okay. So suppose this claim is not true. So then there exists an element x belongs to the centralizer such that the distance between x to the cyclic subgroup is strictly greater than twice distance between 1 to G plus 4 delta. Let us take this to be K, this quantity to be K. So distance between x and the cyclic subgroup, so it is equal to again the distance between 1 and x inverse, the x inverse, the group generated by G. So therefore there will exist y belongs to x inverse this cyclic subgroup G such that the distance is equal to distance between 1 y. Okay. So we have taken this x to be in the centralizer. G also it lies in the centralizer of this element G. And so this will imply that so this y it also belongs to the centralizer of the G. So x belongs to the centralizer of the G. So and y it belongs to x inverse the cyclic subgroup generated by G. So therefore y it will belong to the centralizer of G. It follows from this one. Okay. So therefore yg will be equal to gy. And now consider this, in fact, it is not quadrilateral, it is rectangle. So join 1 to y by a geodesic, join 1g by a geodesic, y and gy by a geodesic. So gy is equal to yg. So this geodesic, it will be labeled by again by the word g, and join g and gy again by a geodesic. So length of this geodesic will be same as the length of this geodesic joining 1 and y, because G commutes with y. And also we have taken y such a way. So in fact, this distance is greater than k, so which is equal to the distance between 1 and y. So distance between 1 and y is greater than k. So therefore, what we can do, so we can take 2 points P and Q belonging to this geodesic, joining 1 and y, such that distance of 1 to P is k by 2 and distance between Q and y is k by 2. And now let us take yt to be the midpoint joining this P and Q. And let us take this distance between y and yt, that is equal to t. Okay, so now observe that there exists gyt prime in the geodesic joining G and Gy such that the distance of yt to gyt prime is less than equals to 2 delta. So how you can do this thing? So you can join this 1 and gy by a geodesic, and if I take this point yt, so I'll get either a point here or here, such that the distance of those distance of y2 to this, either this point or this point, is less than equals to delta. So I'm taking this triangle 1y gy, and this triangle we know it to be delta slim. So either this distance will be less than equals to delta, or this distance will be less than equals to delta. Now suppose this distance, if it is less than equals to delta, so then distance between yt and y, so this will be less than delta plus distance between y and g. So yeah, so then distance between y and yt, it will be less than k by 2. So what is this k? So k is twice distance between 1g plus 4 delta. If I take k by 2, it is k by 2 is equal to distance 1g plus 2 delta. So we'll have a contradiction. So we'll have a contradiction if this distance of yt to this side is less than equals to delta. So therefore we'll get a point here such that the distance will be less than equals to delta, and similarly by the same reason there will exist a point here which I have called it to be gyt prime. So this distance will be again less than equals to delta. So there exists a point gyt prime, the geodesic joining g and gy, such that distance between yt and gyt prime is less than equals to 2 delta. And also observe that distance between y and yt prime, so this will be equal to t prime. So distance between g and gyt prime is equal to t prime. So therefore, and that distance is equal to distance between y and yt prime. So therefore, distance between yt and yt prime is equal to t prime. Okay. Okay. So again, so I have done it here. So from here, so what you can show that distance between yt and gyt is less than equals to 4 delta. So this I am not doing. So here I have said the reason. So this will imply the distance between yt inverse gyt. So this is less than equals to 4 delta. So thus a conjugate of g lie in the ball of radius 4 delta around 1. So this is a contradiction because what we have assumed that, so we can assume that the any conjugate of g does not belong to this ball. So because of that thing, so what we have, distance of x to the cyclic subgroup is less than equals to twice distance of 1 to g plus 4 delta. And this is true for all x belongs to the centralizer of this element g. So this will imply that this index, so this is finite. And the next theorem, it says that, so I'll not prove it, you can I have given the proof. You can read it from here. So it says the following. So if I take an infinite hyperbolic group G and N to be an infinite normal subgroup of G, if N is quasi-convex in G, then N has finite index in G. So that is the quotient group. G mod N is a finite group. So the proof is written here. You can read the proof from here. Okay, so I'll stop here.